So the next element we're going to talk about is helium. And this has 2 electrons. So what I'm going to do now is write out an incorrect configuration for helium to make a point. So this, what I'm writing is wrong. I'm going to erase in just a second. So we have the 1s orbital in helium, and it'll have 2 electrons. And so what I'm writing is wrong. I'm writing 1 arrow up, and I'm writing the second electron with its arrow up as well. This is wrong. And so why is it wrong? It's wrong for 2 reasons. One is that when you have a pair of electrons in an orbital, they must be spinning in opposite directions. So if you have one that is spinning clockwise, as indicated by an upward arrow, the other electron must be spinning counterclockwise. And so we would indicate that by flipping over this arrow and have it point downward. Now there's another reason why this is wrong. So let's say we were to write the quantum numbers, the 4 quantum numbers for this electron on the left here, the one that's pointing up, or this one on the left. So n is 1, it would be this. N is 1, it's an s sublevel, so it's 0. There's only 1 orbital in the s sublevel, so the next quantum number is 0. And then this arrow here is pointing up, so it's a electron spinning clockwise, so it's going to be plus 1/2. So that would be the quantum numbers for that electron. Now this electron will have quantum numbers too, but look, it's in the same orbital as this first electron, and it's also spinning in the same direction. And so it will have exactly the same quantum numbers. Now there's a rule in quantum chemistry that says that whenever you're looking at electrons in an atom, no 2 electrons can have exactly the same 4 quantum numbers. They must have different quantum numbers. All you need is to vary one of the quantum numbers, and then that would be fine. So this cannot exist because both of these electrons have the exact same set of 4 quantum numbers. So this cannot possibly be true. So I'm going to erase this and draw the correct electron configuration of helium. So it's going to be 1s, and then the first electron is in the 1s orbital and spinning clockwise, and the next one must be spinning counterclockwise. So that is correct. So this is 1s2. And so now what we can do is write out electron configurations for these electrons. So for this first electron here, it's exactly the same it's exactly the same quantum numbers as this hydrogen's electrons because it's in the same orbital and it's also spinning clockwise. So it is also 1, 0, 0 plus 1/2. The quantum numbers of the next electron over, it's in the same orbital, so these first 3 quantum numbers, if it's in the same orbital, must be the same, but it's spinning in the opposite direction, it is negative 1/2. Now, what is the Lewis dot structure for helium, or notation for helium? So you write the elemental symbol, which is helium, and so we check the highest energy level of helium. We only have one energy level here that has electrons, which is the highest. It's the first one. And so there are 2 electrons there. And so what we're going to do is put a pair of electrons like that to indicate the 2 electrons in the first energy level. Now, is it paramagnetic or diamagnetic? So recall that you have an element that is diamagnetic if all of the orbitals that are occupied by electrons have a pair of electrons in each of the orbitals that are occupied by electrons. And so here we have a single orbital that's occupied by electrons, and there's a pair here. So this must be diamagnetic. Okay, now another thing I want to kind of briefly digress and talk about, which is very important, is you should know that helium is very stable. It is very stable and has low potential energy, and therefore it's unreactive. And so helium atoms tend not to react with any other elemental atoms, and they don't react with other atoms of themselves. And so you already know one reason that this is true is because helium is a noble gas. But there's actually a more important reason now which you can understand. So you will have a very stable, low energy, potentially very unreactive element if the highest energy level that has electrons is filled with electrons. And so what you can see is that the highest energy level here is the first energy level. There's only a 1s orbital in the first energy level. There are no p or d orbitals, so there's only one orbital to fill in the first energy level, but it is filled with electrons. And so the highest energy level is filled with electrons. And then when you fill up an energy level with electrons, that makes the element very stable. And so that's why helium is stable. Okay, so we're going to move on to lithium. And there are 3 electrons in it. So let me just do the orbital notation for this. And so there are 2 electrons in the 1s orbital. The third electron goes into the next orbital up in energy, which is the 2s. So that is the correct configuration. And so what is electron configuration notation? It's 1s2, 2s1. How about the quantum numbers? Well, this first electron here will have a set of quantum numbers which is 1, 0, 0, 1/2. This next one here is going to be 1, 0, 0, negative 1/2. How about this one here, this one electron in the 2s? What will its quantum numbers be? So you can see now we have an electron in the next energy level up in terms of energy, which is the second. So n is the energy level, so n must be 2. So for this electron here, its quantum numbers are n is 2. It's still here in the second energy level, electron is going into a 2s orbital. And so an s orbital or s sublevel has a value of L that is 0, that is always set. Therefore, it has a value of m sub L, which is 0, because there's only one s orbital. And if it's 0 in L, it must be 0 for m sub L. M sub s, it looks like it's an electron pointing upwards in this diagram, so it's spinning clockwise, and so it's going to be plus 1/2. So these are the quantum numbers for this electron here. So a lot of times people put in brackets around the 4 quantum numbers, and you're welcome to do that, and I've done that there. Okay, so what is the Lewis dot structure for lithium? So lithium has now a total of 3 electrons. But remember, when you are writing out a Lewis dot symbol for an element, you only consider the electrons in the highest energy level. So lithium, although it has 3 electrons, they're going into 2 energy levels. The highest energy level is the second energy level, and there's only 1 electron there. So again, with the Lewis dot structure, we only consider the number of electrons in the highest energy level. There's only 1 there. So lithium only has 1 dot. Now, is it paramagnetic or diamagnetic? Well, here is a situation where we do have an orbital that has only 1 electron in it. And so that would allow that element, lithium, to be attracted to magnetic fields. So it should be paramagnetic. Okay, the next one is beryllium. And there are 4 electrons here. And so the 2 orbitals that are filled up are the 1s and 2s, like this. And so the electron configuration is 1s2, 2s2. I'm hoping you can figure out the quantum numbers for each of these 4 electrons of beryllium on your own, so I'm going to skip that. So what is the Lewis dot structure for beryllium? And so again, we consider only the number of electrons in the highest energy level, which is the second, and there are 2 electrons there. So I'm going to write beryllium here. Now with helium, there are 2 electrons in the highest energy level. I kind of put them together to sort of remind myself that helium is a stable atom. But with beryllium, that is not quite the case because there are empty 2p orbitals here that are not filled. So this is not as stable as helium. So to indicate that there are 2 electrons in the highest energy level, but it's a relatively unstable atom, I'm going to put 2 electrons there like that. Okay, so is it paramagnetic or diamagnetic? And you can see that all the orbitals with electrons in them have a pair of electrons, so it should be diamagnetic. Okay, so the next one is boron, 5 electrons. What is its configuration? So 1s is filled, 2s is filled, and then 2p are the next orbitals up in energy that get filled, and you just put one electron here in one of the p orbitals, and you by convention we fill up this first line with an electron. Can you write out the quantum numbers for this electron? Well, what that would be, I'll put in brackets here. We have here for this electron, it's in the second energy level. It's in a p sub level. It's no longer an s sub level. This one is in a p sub level. So L now is equal to 1. Now, what about m sub L? So recall that m sub L can have values from +1 to 0 to -1, because L is 1, and so you have values from -L to 0 to +L. So it's -1, 0 to +1. So you might say, well, okay, this is the first one, so maybe -1. You actually can pick any one you want. You can write in -1 or 0 or +1. It doesn't matter which one you choose. It will matter if maybe you have multiple electrons here and you're trying to distinguish them in the 2p sublevel, but if you only have one, it really doesn't matter. So I'll just pick one, so I'll just say -1. It looks like it's spinning clockwise, and so I'm going to put +1/2. Okay, so what is the Lewis dot notation? Well, again, it's going to be the symbol with the number of electrons on the highest energy level, and so there are 3 there. It would look like that, and it looks like it's paramagnetic. Okay, so the next one is carbon, and this has 6 electrons. This is a little bit trickier. So you have 1s, 2s, and then you have 2p. Okay, so there's 6 electrons. So the first 2 go into 1s, first 2 go into 2s. Now the 2p, so the first electron goes here, but where does the next final electron on carbon go? Does it go pair up with this electron here, or does it go into the next orbital there? Well, there's a rule called Hund's rule, which says is that if you have multiple orbitals that are degenerate, meaning they have exactly the same energy, you put one electron in each orbital before you put a pair in one orbital. So what we're going to do is if we have 2 electrons that go into 2p, because of Hund's rule, we must put this electron here in one of the other 2p orbitals, because again, the 2p orbitals have the same energy, they're degenerate. Okay, so I'm going to skip the quantum numbers, but I'm hoping you can figure those out if you wanted to. And then I'll write the Lewis dot structure here. And then it looks like this will be paramagnetic. Okay. What I'm going to do now is we're going to skip nitrogen and move on. So I'm going to give myself some space here. Let's go on to oxygen, which is 8 electrons. So orbital notation, 1s, 2s, 2p is next filled. There are 8 electrons, so 2 go in the 1s orbital, 2 go in the 2s orbital. And then this is the 5th one, the 6th one, and we put the 7th one here because of Hund's rule. And then the 8th one, now you can have a pair in one of the orbitals. And by convention, we put it on the first of these orbitals of the ones that are degenerate. So that is the orbital notation for oxygen. So what is the electron configuration notation? It is 1s2, 2s2. It looks like we have 5 electrons in the p sublevel, so it's 2p5. How about quantum numbers? Let's just take this one electron here and see if we can figure out quantum numbers for that. Okay, so this electron here will have a set of 4 quantum numbers, which should be different than all the quantum numbers of these other electrons. And so it looks like it's in the second energy level, so n is equal to 2. L is going to be equal to 1 because it's a p sublevel. M sub L, well, your choice is either 1, 0, or -1. So if I had, for example, m sub L of this electron pointing up here, and this orbital would be +1, and I had this one set to be 0, then I would set this one to -1. So I can set this one to -1 knowing that these other 2 electrons in the 2p sublevel need to have a different value of m sub L. And so here the electron is pointing up, and so it has a clockwise spin, so it's +1/2. Okay, so what is the Lewis dot structure for oxygen? So you're looking at the symbol here for oxygen. And so it'll have as many dots as electrons in the highest energy level. And so it looks like we have what? The highest energy level, be careful here, a little bit more difficult to see. We want the highest, numerically, highest number energy level. So 2p is a higher energy sublevel than 2s, but they're both part of the second energy level. And so we're considering energy level here for highest energy level electrons. So the 2s, 2p, these are the highest energy level electrons. So there's 2, 4, 5, 6. So it needs 6 dots. So I'm going to draw a pair here, and then 5, 6. And this looks like it's going to be paramagnetic. Okay, so next we're going to do fluorine. I'm going to just erase this to give me a little bit more room. Okay, so fluorine is 9 electrons. So this is 1s, 2s, 2p, 2 electrons here, 2 electrons here, 5, 6, 7, 8, 9. Okay, so that's the orbital configuration for fluorine. Electron configuration notation is 1s2, 2s2, 2p5. How many electrons does fluorine have in its numerically highest energy level? It's all the electrons in the 2p and the 2s. So it looks like there's 2, 4, 6, 7. So fluorine should have this Lewis dot structure. And this is paramagnetic. Okay, how about neon? So this has 10 electrons. So its configuration is 1s, 2s, 2p. And I think what you can sort of see here is we have enough orbitals written out at this point. There are a total of 6 of them. Wait, excuse me, 5 of them. I can't count. There are 5 orbitals here, each accepting a pair of electrons for a total of 10 electrons. And so its electron configuration is 1s2, 2s2, 2p6. And so we have neon. And so now we have 8 electrons in the numerically highest energy level. So it's 1, 2, 3, 4, 5, 6, 7, 8. And so this is going to be diagnetic. Okay, so I want to talk a little bit about neon now. Okay, so neon is also very stable. So I'm going to draw a box around it like this. This is very stable, and it has low potential energy and very unreactive. Okay. So the reason why helium was stable is because its highest energy level, which was the first energy level, only had 1 orbital, and you only needed 2 electrons to fill it, so it was pretty easy to fill an energy level. So neon is probably even a little more stable than hydrogen, and the reason is there's a couple reasons. So one thing you'll notice is now at this point we have completely filled up the second energy level, which was comprised of the S sublevel and the P sublevel, with electrons. So the second energy level is completely filled with electrons along with the first. So all energy levels in this element are filled, so that makes it stable. But it's stable for another reason. If you have an electron configuration that has 8 highest energy level electrons, then that is called an octet, and that gives it further stability. And so here what you can see is this highest energy level is second. It has 8 electrons in it, as indicated by the Lewis dot symbol. There are 8 electrons here as around the symbol. So therefore, if you have an element with an octet of electrons, because there are 8 electrons in its highest energy level, then that makes it very stable. And again, if it's very stable, it's going to have relatively low potential energy, and it won't want to react with other atoms of different elements, nor of atoms of itself. Okay, so let's do a few more and then talk a little bit about this. Okay, so I'm going to erase carbon. So I'm going to put on sodium, so you can see that this just continues on and on. And so you'll have the 1s, 2s, 2p. Do you remember what the orbital next that is filled? It's 3s. So here, I'm just filling up the first and second energy level with electrons. And so sodium has 11 electrons. And so the 11th electron goes into 3s. So can you write out a Lewis dot structure for sodium? So the question is, does it have 9 electrons? And the answer for the Lewis dot structure, and the answer is no. It only has 1 electron, 1 dot. And the reason is, again, you'll have as many dots as electrons in the highest energy level. Numerically, the highest energy level now is the 3rd. There's only 1 electron there, so it should have 1 dot. Is this paramagnetic or diamagnetic? And so we have a single orbital here with 1 electron, so that makes it paramagnetic. Okay.